We have a few things to talk about, and we'll start off with discussing this idea of, oh man, now my it's not one thing, it's another. The bias-variance tradeoff. Let me just check the mapping here. Okay. Okay, so we'll start with the okay, and this is a topic in supervised learning. Supervised learning, again, is the idea that you have training data. Okay, so you have training data with the quote correct answers. Okay, so anytime you're dealing with some kind of loss function and you're trying to see if your fitted values match the correct answers or whatnot, that's a case of supervised learning. Okay, and as far as the bias-variance trade-off, we might have this notion of the total, the expected value of the squared error, which our textbook calls M. Okay, it's noted as M in the textbook. We can think of this as the expected value between the actual data Y and basically our Y hats. And we take the squared difference there. Okay, so we can think of this as the expected value of the squared error, and this can be decomposed into the bias squared plus the variance. Okay, and the bias itself, and I'm not going to bother trying to prove or derive this. The bias is going to be the difference between what our model predicts, the expected value between what our model predicts and the actual value, and then the variance of our predictions is kind of the usual definition of the variance. So it's the each y hat versus the mean of y hat squared. Okay, and this gets further split into the kind of the big ideas here. Okay, the bias, you can think of that as the difference between our model and the true values. Between our model and the true values, and this is generally kind of in the test data. And we'll say an overly simplistic model will have a large bias. Okay, and we'll say, it underfits our data. On the other hand, we have our variance. Okay, and this would be our kind of our variance in our estimates. Okay, and we can say models that are too complex high variance, okay? And this will be overfits our data. And so there's always kind of, this is a general idea that we're always kind of trying to work with is, how complex should our model be, okay? So basically the guiding question, or the question that we wish we could answer, so, if you make it too complex, you're going to have high variance, and this is a problem. If you make it too simple, then you'll have high bias. Okay, so there's always this balance and this trade-off that exists. We won't get too much into it from there. Okay, go back, sure. Okay. All right. Here we are in chapter 2 of our textbook. We are taking a maximum likelihood approach, and the reason why we're taking a maximum likelihood approach is that we have explicitly modeled the error that there's an error component in our data, right? So the existence of an error component or a noise term in our model. Okay. And because of this, now we can do maximum likelihood estimation. And also because of that, the estimates that we have, our parameter estimates for our model themselves are a random variable based on the random values observed in our data, right? Okay. Contrast that to using trying to minimize the squared residual function, in those cases, there's no, the estimated model parameters, even though we end up getting the kind of the same term, you know, W x transpose x inverse x transpose t, even though we arrive at the same thing, in those cases, we kind of say, you know, our data is fixed, and we're just trying to find the set of parameters that minimize this thing. There's no variance or there's no uncertainty in those estimates because that data is fixed. Okay. So over here we have, you know, the estimates of our model parameters themselves are random variables based on the random values we observe. So therefore, our parameter estimates have uncertainties. Okay? Contrast this to minimizing the squared residuals. Okay, here in that case, you know, the data is treated as fixed. And therefore, the parameters that minimize our loss function has no uncertainty. And so now we might want to, you know, express what kind of uncertainty we have with our model parameters, the uncertainty in our estimates. Okay, so we'll do some math to kind of take a look at the uncertainty in our estimates. Okay, so. Okay, so, you know, we start off kind of our model for linear regression. Is that, you know, the values we observe is, you know, intercept plus slope times our x variable plus some error term. And the error term comes from normal distribution centered at 0, variance sigma squared. Okay, and so we can say, you know, let's say that the true model that exists in the population we can express this as, you know, a vector product W transpose vector xn plus our error term, okay? And so these are the true parameters that exist in the population. Okay, and therefore the likelihood of our data of our actual data, is the, probability of our entire vector of data given the input matrix X, the true parameters W, and the sigma squared of our error term. Okay, and this in of itself is going to be the product of all of these kind of normal distributions centered at W transpose X with variance sigma squared. We can take this all and put it into the context of a multivariate Gaussian. Okay, so this can be turned into a kind of a multivariate Gaussian. So if you recall the multivariate Gaussian, this would be the normal distribution for the entire. So this is going to be an n-dimensional multivariate Gaussian. Times the I matrix, identity matrix. So this goes down the diagonal wherever so sigma squared I is a diagonal matrix with sigma squared down the diagonal. So if you have lots of data in here, this is the entire thing. All right. So this is let me just kind of pull up the multivariate Gaussian here. Probability of some vector X is going to be D is the dimension of your data, okay, here. D over 2 over the variance covariance matrix sigma, this being the norm of that, e to the You guys seen the multivariate Gaussian before? No. Yes? No? Oh, shoot. Okay. Well, how do we explain the multivariate Gaussian then? So it's hard to picture a multivariate Gaussian in higher than 2 dimensions. Okay? So all right, well, maybe I'll have to have another lecture where we talk a little bit about the multivariate Gaussian. I don't know how to explain this just off of the top of my head. Well, you can kind of think of the multivariate Gaussian as almost like a product of Gaussian distributions. Okay. However, if there's covariance between the things, then it gets more complicated. If everything is independent, then it's easily just the product of this stuff. Okay, let me just do just a quick, very quick overview of multivariate Gaussian. Okay, so we'll say if two things are independent, you can kind of think of, one of these things has a Gaussian distribution that looks like this, and then the other, this could be x, and then, and y comes from a Gaussian distribution that looks like this. And if they're independent, then you end up getting kind of this this thing of, these are supposed to be concentric circles, okay? Or it could be, if one of the variances is larger than the other, then you have these concentric ovals, but they're at right angles to each other, okay? So you have this, I don't know, whatever this type of, it's supposed to look like a hill, okay? You have this kind of shape. If there's covariance between, and this is just with 2 dimensions because I can only graph 2 dimensions, right? If there's covariance, then you'll get kind of these. Is the word still concentric if they're ovals? I don't know. You get this thing where x and y, they vary together. Okay. And again, this is just, if this is just a 2-dimensional multivariate Gaussian. Okay. It's hard to picture what a 300-dimensional multivariate Gaussian would look like. Okay. But it also exists. Yes.
Is that third dimension the density?
Yeah. In these things, the third dimension would be the density. Okay. So right. So over with one dimension we have the x, and then the height is the density. Okay. Over here with 2 dimensions, the height would still be the density. And this is where there's covariance between x and y. Okay. And then so your covariance matrix. XY, which we'll call sigma, will have, in this case, you'll have, this is the variance of x, and down here would be the variance of y, and then over here you have the covariance of x and y, and the covariance of x and y. This is kind of your variance-covariance matrix there. So that stands in for sigma. And you can just imagine if you have a very large data set, then you have all of these things here. Okay, and so the idea being, if they are independent, if x and y are independent, then what is the covariance between the variance covariance matrix here? Yeah, so here it's the variance of x squared and the variance of y, and then over here we have 0 and 0, right? If they're independent. And so the idea here is that all of our observations are independent, and so there's no covariance between our observations, and so our variance covariance matrix is just the diagonal matrix with sigma squared running down the diagonal. Okay, because I guess all observations are independent of each other. Okay, so it ends up just being kind of the product of all of these normal densities together. Okay, in this case, yes.
For the, I guess the denominator at the very front of the multivariate Gaussian, is that just like the square root of the element of the covariance, or?
If you have a diagonal matrix, yes.
And what if it's not that?
Then I don't. I don't know. It's a lot harder. It's the matrix times itself gives you, it's the idea of it's a square matrix, right? And so if you have, oh wait, no, this is the, oh, you're catching me off guard here. This is the norm of the matrix. So it's a magnitude thing. So then it's fine. Oh, I'm a little bit rusty on this, so I'm sorry. Okay. So anyway, we have this big data set, and we do it. Can I just wave my hands and say this is what we get, or yeah? Okay. As long as I don't expect you guys to derive it yourself, right? So, well, basically, if we, so we'll say, we model, we model our data as the result of a, probability distribution itself. We model our data as the result of a probability distribution, and in this case, it's the multivariate Gaussian. Okay, and as such, we can calculate the expected value of our parameter estimates okay, w hat, right? So we have the vector w hat. Should I do w hat with the vector over it? I don't know. How should I do this? Is that more correct? I don't know. Huh? You like the second one? Okay, we'll go with the second one. Okay, so we'll do that. Okay, so we can model the expected value of this thing. All right, and so the expected value of this thing okay. Well, we have to do the integral of w hat times the kind of the probability, dt, et cetera, et cetera, et cetera. Okay, and anyway, we'll skip the math, and it turns out the expected value of our estimates is the original, the true model parameters itself, okay? So the nice result, the result shows the expected value of our parameter estimates are the true parameters. Okay, that is to say our model estimates, our parameter estimates are unbiased. So that's a good thing, okay? That's a good thing. We can, given any random data set, this random data set might give us parameter estimates that are too big or too small, but in the long run, if we had lots and lots of random data sets coming from our population, and we use those to model our parameters or come up with estimates of our parameters, in the long run, our parameter estimates will be centered around the true value of the actual parameter estimates, okay? So, I'll just say on any given data given random data set may be too big or too small, but the expected value is correct. Okay, then we can talk about getting the covariance of all of this. I'm debating in my head how much detail we want. Okay, so let's now let's take a look at the covariance, or basically the I'll just say the uncertainty in W hat. Okay, and so this is our variance covariance matrix, or so we can try to estimate the covariance of W hat. Okay, and so basically we're going to use the covariance definition of the covariance, which is basically the expected value of W hat squared, which is going to be W hat transpose, minus the expected value of W hat itself squared. Okay, expected value of that. And because of because these themselves is W hat, or is W. I guess there's vector arrows over everything. This ends up just being kind of W hat squared minus W squared, which is WW transpose. Okay. All right. I mean, this is, you know, if you just think back the definition of the variance of x, it's the expected value of x squared minus e of x quantity squared. It's basically this, except we have a multi-dimensional thing, so it's going to be covariance, and because it's vectors, we can't just put squared. We have to do like this WW transpose business. Okay. All of page 80 in the textbook covers all of the math here. We'll skip down to the result, which is what I want to talk about. Okay, so page 80 covers all the steps. I won't expect you guys to like memorize these steps or anything like that. Okay, covers all the steps. Maybe good to check out, but don't worry about it. All right. Okay, so the result gives the results that the covariance of W of our estimates, okay, is our X transpose X inverse. Okay. All right. So this tells us the uncertainty of our parameter estimates. Okay. I'm going to kind of skip the equivalence here but this ends up being also equal to the second derivative of the log likelihood. Okay. So the covariance, this is also equal to, it's called the Hessian, okay? The Hessian matrix of the log likelihood. You can think of the Hessian as the kind of the second derivative of the log likelihood with respect to the vectors W. Now what does this even mean? Okay. This is this tells us how much uncertainty we have in our parameter estimates W hat. Okay, so if this thing ends up being quite large, that would tell us that the estimates that we have W, okay, could vary quite a bit based on the data that we've seen. I'll give you a little bit more formal definition. Oof, we're gonna run out of time here. But basically, let's just say your data, the data looks like this. Okay, so you got and so you fit something that looks like this. Okay, this is your fit here. Basically, what this is saying is that in this case, we would not put just looking at this. Okay, we would recognize that there's a lot of variation in the data that we have, okay? We recognize that the estimate we have, the estimate of the line, is very dependent on the data we see, okay? Because if we generated another data set from the exact population, okay, another data set from the same population could give us a wildly different line, right? Maybe not wildly different, but it could be something as different as this, okay? Two different data sets from the same population could give us significantly different lines, right? Another data set could give us a significantly different line. Oh shoot, I'm sorry. I blame the projector. Okay? Whereas if our data set, the current data set, our data set looks something like this, okay? Our fit would look like this, and if we generated another random data set from the same population, it might differ, but the amount of that line differing will be very small, right? So if this is our data, okay, our estimates of W, I guess W hat, will not produce wildly different lines. Okay, so that's kind of the conceptual idea, we'll explore this a little bit more further on Friday. But this is kind of where we're headed. Okay, so we'll end there for today, and I'll see you guys on Friday.